All right, good morning. So I hope I convinced you that inductors and capacitors are quite amazing devices and they can do very useful stuff. We've tried to solve this problem before, right? We have an outlet, 110 volts or something like that. If we plug that directly into a cell phone, well, all we get is sparks and a dead cell phone. So we need some kind of a device that drops the voltage down from 110 volts to something reasonable, like, for example, 10 volts. That's the example that we calculated through last time. And a voltage divider obviously can do this, but the problem with the voltage divider is that most of the power actually gets burned up, right? Most of the power that we get out of the supply just becomes heat, and it doesn't power our cell phone at all. And that, of course, is very bad. In that particular case, it just makes for a very, very hot charge. If you touch it, you get burned. It also, I guess, given the number of cell phones that are in use and similar devices, it makes for really sort of an environmental problem. If we were to use voltage dividers in these things, we would use considerably more power and many more power plants and so on, much more global warming. Obviously, if you were to charge your phone from, let's say, a laptop battery or so, then it would be even worse because it would run out of power very quickly. So we need better solutions, and hey, miraculously, inductors and capacitors, they can do that. So let's just very quickly look at the solution that we looked at here. I don't want to go through the circuit completely again, but what we really are doing is we are sort of setting up a current in the inductor by closing that switch, so power gets transferred from the source into the inductor, and then afterwards, when we open the switch, the current keeps flowing now through the diode D1 and through the load because the inductor has stored energy, right? And in doing that, and again, I don't want to go through that we can in a way transform this voltage from 110 volts down to anything we want. And in fact, it's a very easy way to adjust what the output voltage is going to be. Given the input voltage, how do we adjust the output voltage that appears across the device that we want to power? We saw that just at the end of last lecture. How did you do that? Yeah? Exactly. We simply need to control how long we close the switch and how long then we leave it open. By changing that ratio, we can set the output voltage. That's, of course, very convenient because then we can easily adjust that. Okay, now I'm somehow getting to work here. So. All right. So somehow all this extra power dissipated in the voltage divider must have made me warm. Okay, so there is one last problem that we need to address here. Okay, so one thing, I think we didn't talk about that yet. How big an inductor should we make? Right? We found out that miraculously in this circuit, what we really want to do is set the output voltage, right, given any input voltage value. It doesn't depend on the size of the inductor at all. So the question is, how should we choose the inductor? And whenever we have such a question as engineers, what is the first answer? Exactly, and what would that probably be? Very small, right? Basically, just a stub of wire. Okay. So, does anybody remember from the equations that we went through why that perhaps wouldn't work? It's always the same tool. Oh, here's somebody in the middle. Okay, yes. Okay, that's so that's the right answer. So here was this current that was flowing through the inductor. And we never actually calculated the current. We calculated not the current, IL, we calculated delta IL. We calculate how much it was changing. And so it was changing up, and then it went down, up, and then it went down, right? And this, the height here, that was delta I. And how much ripple do we want? Well, we found that this delta IL was equal to Vs minus V out over L1 times the time T1. Okay? So given that, of course, if we choose a certain frequency at which we want to operate, that's also an interesting choice. We don't want to get into that. Obviously, faster makes it that these ripples are at really high frequency, and so that's nice. On the other hand, making the circuit go at a very high speed actually dissipates more power because we need to turn on and off the switch, and that costs a little bit. So, yes.
Well, this is a side question, but how does one make such a square wave that goes on and off really quickly? Like in the lab, you control this thing with a square wave.
Yes.
Like how does one create such a wave in the timings that we'd like to use?
Well, you saw in the laboratory you can use a 555 timer, and you change somehow resistances, and you can make any kind of pattern, right? So we will see another way that probably in this case would be used to build a little microcontroller, at least some digital circuit that does that. But the 555 timer could do this. So you would have a solution. If today you had to build this, you could do that. And in fact, in Lab 5, you're going to build this thing, but then in order to make the lab a little bit simpler, we're actually not going to use a 555 timer. We're going to use the function generator, simply because that way we have to put fewer components onto a prototyping board, and there are fewer chances for things going wrong, and therefore there is a better chance for you finishing in 3 hours. Right? So we think about that when we design the labs. Okay, so we get this waveform, and based on that, we find that, of course, we can turn this equation now around. If we solve for L1, we get the source voltage minus the desired output voltage over delta IL times T1. And so, for example, here we had 110 volts. We wanted 10 volts. And then how much ripple do we want? Really, that depends, of course, and we need to understand more about our application. But for example, 10 milliamps, and then we had 0.1 microsecond. That's what we had chosen for T1. And out of that, we get 0.9 millihenry. Okay, so the numbers are not that important, but I guess what is important is that, yeah, of course, it's not that it doesn't matter what L is. It doesn't matter for when we just are interested in the output voltage, but of course, we also care about the ripple in practice, and that sets a certain value for the inductor. Okay, we will skip that this time. Second order systems. Those are when we have an inductor and a capacitor simultaneously. So then we get second order system. Very interesting stuff's happening. Before we've looked at when we have a first order system, just an inductor, just a capacitor, then we get some kind of an exponential decay, right, when we hit it with a step. Right, so we turn on the voltage, and then the current goes up, and then the current decreases. And if we have a second order system, much more complicated stuff can happen. For example, we sort of see, if we look at this picture, we see the exponential decay, but we see that it also rings. There is also an oscillation. It's not somehow a timer circuit or so, or a synthesizer that made this. It's just a capacitor and an inductor together. If we hit them with a step, they can produce such waveforms. Okay, so those would be second order systems. If you're interested in them, there is a bit of write-up on the in the book. You can find them in the book, but we'll not go over that mess this time. Okay, so what should you know by now? Well, capacitors and inductors are characterized by differential equations. I would like that you know these differential equations. No cheat sheet for that. In particular, I would like you to understand what these differential equations really mean for the circuits, right? And we looked at this in more detail, but for example, it means that the inductor resists current change. If we make some abrupt change, the voltage across the inductor, it does whatever it has to do. But the current cannot change abruptly in an inductor. And with the capacitor, it's very similar, except just the dual. It's the voltage that doesn't make a jump. The current can make large changes. And based on that understanding, you should be able now to analyze circuits with inductors and capacitors and switches. And again, why is this interesting? Well, it's interesting because then we can build stuff like this voltage converter, right? This power supply, power brick or so. Okay, and so we should be able to determine boundary values. What is the current? What is the voltage for before and after switching? What happens as the time if you wait for a very long time? You should be able to write differential equations for any RLC circuit and determine initial conditions. We have looked at, and then you should be able to solve first-order differential equations. We have not looked in this course at how to solve second-order and higher-order differential equations, but you should be able to write, of course, down the differential equations for any kind of a circuit. Okay? Are there any questions about that? So you really know. So these are the questions that I have. In order to save some time, we'll do those Monday. But so I would like you to be now able to solve questions like these. And actually, E brought along a whole pile of sheets of paper. But we will not do this today. We will do this Monday. So, but something like this, you should be able to solve now. And if you don't, well, come and ask us. Okay. All right. So. With that, let's switch to a new topic. Yes. Oh, now the questions come. Good.
When we're talking about RLC circuit, mean only second-order circuit?
Only first order. These circuits that I just showed here, these are first-order circuits. Yes.
Because they have only
well,
or inductor circuit?
Only one. I mean, it is a little bit more complicated whether you get a really first-order circuit is where when you write a differential equation, you get only the first-order derivative of the variable, be it voltage or current, that you're interested in. Okay? If it's a second-order circuit, you will get the first-order derivative and the second-order derivative. It's exactly the same nomenclature as you used in math, right? In math also you had first-order linear differential equations, you had second-order linear differential equations, then you just had linear differential equations and probably Euler equations and so on, right?
We will do that only if there are both inductor and capacitors.
Yeah, even if you just have capacitors but multiple ones, you can make second-order systems. If you separate the capacitors with resistors, you get that. Okay? So you should be able, using sort of node voltage analysis techniques, for example, or basically KVL and KCL, you should be able to write a differential equation for any kind of a circuit. Okay? But then we did not go through the mechanics on how to solve this differential equation, except for the first order. Okay? First order, where you just get an exponential increase or an exponential decay or so, that we talked about how to solve, and that you should be able to do. Okay? Yes?
In real life, do you actually ever use anything more than second-order circuits?
Oh, yes. In practice, of course, most circuits we build are very high order. Why? Well, because when we make all the wires and all the interconnects, we have all these parasitic capacitances and inductors and so on. That last time I argued, if we want to understand what's going on, we leave away. And so in practice, circuit design usually deals with very complicated circuits that are of very high order. Then we do just like we did in last time. We try to understand how the circuit works, and we somehow simplify. We say, well, it's really this effect that really matters most, right? And that we are most interested in. And then we can analyze it. That will be a first or second order circuit usually. And then afterwards you use SPICE, the circuit simulator, to verify. And then if the circuit simulator agrees with what we've calculated, well, then all these higher order terms really are not significant for our application. But of course they are there, and sometimes even SPICE has difficulty with really high order circuits, because what we really build is very complicated. Right? So incidentally, that is one of the challenges that we don't have very much in EE40 yet, but this problem that the reality is very, very complicated, and yet we need to somehow come up with a solution, right? And so we need to understand what is it really that we can focus on. So in later courses, 140, 142, and so on, you will find a lot of that. 240, yeah.
Just confirming, so we're expected to solve differential equations?
First order differential equations, right? Like you've done, for example, in the laboratory in order to solve the time it takes for your timer to switch and so on, right?
I mean, including the one that has a non-zero constant.
It's just any first order differential equation, right? That you get. You build any kind of a circuit with resistors and capacitors and the source that you switch in or out. Well, there is one other thing, just if you want to get technical. Of course, in a first order equation, the stimulus could be anything. It could be a sinusoid or a sawtooth or God knows what. And we really have only constant, basically steps as stimulus, right? Because we switch in a source or we take it out. And again, we found that even with this simple stimulus, we already can get quite interesting. We can understand and design quite interesting circuits, right? That's why we do that. In math, I'm sure you went over this homogeneous and the particular solution of differential equation, very complicated well, that's good for math, but we don't need that, fortunately. So we have actually a simple case of first-order differential equation that we deal with. And in the exam, you can be sure, in the whatever quizzes we will have, and certainly in the midterms and final exam, you can be sure there will be first-order differential equations of that kind. But I will not somehow stick in another one that we haven't solved here in class, okay? Really, the stuff I'm interested in is the circuits, and that we need a little bit of math. Well, we'll need to. Okay? Makes sense? All right, so with that, new topic. Microcontrollers. I will pick up pace a little bit. So if you start looking at the screens of your computers, or if you start falling asleep or so, I will go faster. Because I think that you know this stuff already. And actually, many of you will know quite a bit of the stuff that we'll start talking about here already. So if I go too fast, if you have questions, well, it's up to you to interrupt me and ask. Okay? So why are microcontrollers interesting? Well, here is a very, very simple application. I actually recently bought one of these flashlights. Unbelievably expensive, like $50, but hey, that's how you make money, right? But that flashlight can vary the light intensity that comes out. And it also has a nice feature that if I leave it on and forget to turn it off, after a few minutes, 10 minutes or so, it turns itself off automatically, and so the battery survives a little bit better. Okay, and so what is inside here? Well, I searched around the web and so on, and some people, they didn't want to pay the $50, I suppose, and so they built it themselves. And what is in here that looks like a 555 timer, it almost is a 555 timer, but it's actually a microcontroller. What does it do? Well, under program control, it turns on and off the light, of course, at a very high rate, right? And also inside it somehow keeps time. It keeps track of the time, and so after 10 minutes, it says, well, you know, if after 10 minutes, either it turns off the light, you have to switch it on manually again. Okay, so that kind of behavior, of course, you could implement with this a couple of 555 timers, but if you wanted then to, it would be getting a little bit complicated. Turns out if it's a microcontroller, you can write a little program that does all of that stuff. Okay, so that's why microcontrollers are very, very helpful. So microcontrollers are also used very liberally in all sorts of devices that we own. For example, a cell phone like this one, or a smartphone, has inside a computer, of course, that does all the wonderful graphics and all of that. But in addition to that, a reasonably powerful computer, actually rivaling a PC of just maybe one generation behind, in addition to that, it has all sorts of other microcontrollers. For example, they're responsible for the touch interface, right? There is a microcontroller that deals with sort of figuring out all of the touch. There is probably a sound compression engine, and so on and so forth. So there are maybe 3-4 microcontrollers inside that support the main CPU that does all the graphics and so the complicated stuff. Likewise, in a car, of course, you will have somehow the navigation board computer. So when you graduate from here, we'll get a great job and you will buy one of these cars, right? But around all of these and the engine control computer and so on, but around all of this you have in a higher end car, you have like 100 little microcontrollers that take care of all sorts of things like the airbags and whatnot. Okay, so actually an electronic system looks kind of like this, right? So around here are kinds of electronic systems, and then what we have in the center is some kind of a digital machine usually. Okay? So some kind of a digital computer, so again in the smartphone that will be a fairly powerful processor, surrounded with additional smaller microcontrollers that take care of all sorts of little pieces here and there. Okay? And then around that, of course, we have all the input and output, the stuff that really makes this interesting. Who would buy a smartphone that wouldn't have any way to communicate with you, right? Hey, if you can't talk into it, if you can't listen to it, if you can't look at the screen, if you can't manipulate the screen, the thing is a dead paperweight. Okay, so around it we have all of these circuits, obviously power supply, we have the clock, the touch sensor, light sensor, speaker, sound amplifier, and so on and so forth. We have all these analog circuits, or largely analog circuits that really make this thing useful. Okay, so before we, I guess, focused on the green stuff, and now we will focus on that blue stuff. And in practice, of course, we need both. You cannot just have the digital stuff because there would be no input, no output, and so on. And you can't, also if you just have wonderful touch sensors, but you have nothing to do with the information, that's also not so good. So the first thing we'll have to deal is look at analog and digital signals. So this, for example, is an analog signal. It can change as a function of time. It can take on any voltage, right? Any voltage between, let's say, 0 and the supply, whatever, 3 volts, can go to any of these voltages. A digital signal cannot do that. A digital signal can have only a finite number of different values. For example, digital binary systems, the ones that we deal most often with, they can assume only one of two possible values, 0 or 1, or 0 volts and 5 volts or so. So a digital system can only have either this value, or then it can go down and have this value and be at that something like this. Okay? And of course, when we then actually build them, there is going to be some transition, but we are usually not interested in the transition except that it should happen fast. Okay? And there is also a clock in a digital system. We talked about that yet. So digital binary data, and again, you probably have heard of this stuff, right? The binary data, every wire then carries only one of two values, one bit of information, that's what it's called. It could be yes, no, 0, 1, smoke, no smoke, and so on. And then again, the encoding. When we actually built the system, we could have 0 volts or 5 volts or whatever, 0 and VDD. We could have current or no current, and all sorts of other versions are possible. Now, obviously, being limited to just 2 possible values is a little bit restricting, but fortunately it's trivial to extend binary systems to more values. Simply if we have more than 1 binary variable, then we can represent as many different values as we would want. So here is shown the trivial example with 2 binary signals, the first one and second one, and they can be both either 0 and 1, and together we get 4 combinations. You probably have seen that, right? Okay, and so there is also then, of course, the further issue that we like to deal with decimal numbers, and these binary systems, well, they are best represented with binary numbers, and so we have to convert. And again, this is probably something you've seen, so I'll skip that. So now let's get back to the microcontroller. A microcontroller, first of all, has basically a computer inside, just like the computer in your laptop or so. It has some kind of a CPU that knows how to add and multiply. It has registers and so on. Stuff that you learn about in, for example, CS61C. So if this sounds puzzling, then just stay for another hour and you will get that story. But in addition, and the stuff that we are here really interested in, the microcontroller has all sorts of circuits that allow it to communicate with the external world. In particular, it has analog digital and digital analog converters to actually deal with the surrounding analog world. Okay, so we will talk much more about this stuff here, and basically we'll leave this to. It's very important, but we'll leave this to other courses. The microcontroller is a big business, very important, lots of applications of them, and it's not too surprising that everybody and his brother is somehow trying to be in the game. And so here's a list of companies that I downloaded from Wikipedia that offer microcontrollers. Usually they're very, very small chips. Here we're going to use one in Lab 6 that's going to be sort of big, but it's very hard to even find those because most people, they want really small ones, so they look something more like this. They have like 20 pins or just a few millimeters square big, right? And they can cram in quite a sizable amount of compute power. Unfortunately, these smaller pitch packages, we can't use them on our protoboard, and so again, in the lab, we are going to use the bigger ones. But really, when you think about microcontrollers, you have to think about the spec that is tiny compared to your fingernail, and I'm talking about the small fingernail. Okay, so it's tiny. It's also very inexpensive. Some of these they cost less than $1. So the one that you use into an electric toothbrush or into a flashlight or so, they cost less than $1. Right? So here are some of the specifications. This is a particular one, the one that we use in the laboratory. There are hundreds of different versions available, and they really distinguish themselves by some have only a very small number of inputs and outputs, and others they have maybe 100 or so. They go at different speeds, 8 megahertz all the way up to 150 megahertz. How would you choose this? What's the best thing? Well, if you buy a new new laptop, which one are you going to buy? The fastest one, probably, right? Probably you buy the fastest one. Why would you bother buying a slow one? Exactly. Especially power is probably the most important thing. The cost is another thing. It may cost actually a little bit less money, but mainly it's going to dissipate less power. In fact, it may not even cost less money. Maybe even pay more money because there are additional features inside that make it dissipate less power. Okay? So fast is not always good. Storage, same thing. This is where you store your memory. How much storage does a laptop have today? Gigabytes, right? Well, here you have a few hundred bytes to maybe a few hundred kilobytes at most, right? But you can, the touch controller doesn't need even that much, no problem. Same thing, data storage and so on. And then multiplier, obviously your laptop has a multiplier inside the CPU. In fact, many of them, several of them. For these microcontrollers, that's an optional feature. So some of these 160 versions, they will have one, and others, they don't have one. So if you need to do multiplication, well, you need to do shifts and adds. And if you need lots of multiplications, well, then you buy a version that has a multiplier. Likewise, floating point usually not in there. But we don't need that. Why would you need floating point for many of these applications? So again, here, that's how it then looks on the website, right? The big tables with 100 and then or more entries. So again, we've talked already about input-output. Obviously, we can have digital input and output. Just set the pin high or low, or look, is it high or low? I mean, basically, is it 0 volts or 5 volts or whatnot? Then analog input, we talked about that. Then suddenly we can convert to any voltage between 0 and VDD. And then there are all sorts of special purpose circuits, input and output circuits, for example, timers on there. So if you get one of these, you don't even need to use a 555 timer anymore. Okay, so digital output, very simple. There are some instructions. You have to look those up in the data sheet. It's a little bit different for everyone, but in principle, it's always the same. You can the pins on the periphery of the microcontroller have some names. For example, port 1, bit 7 or so. And then you can tell the thing, hey, set it to a 1, set it to a 0, or flip it for what you had before. Something like that. All right. And then, of course, you can write programs. You will have, in Lab 6, you will have to write little programs. Will tell you more or less how to do that. And I expect that from CS61XXX, you more or less know how to program. Here we use a language called C. You may have used other languages, but the part of the dialect that we use, it will look very familiar to you. Okay, so something similar for digital inputs. Conveniently, digital inputs have something called a Schmitt-Trigger at the front. What is a Schmitt-Trigger? Yeah, it's something that uses positive feedback, and it really makes it that we really determine, is it a 1 or a 0, and we don't go and flip between 1 and 0, right? So conveniently, these circuits already built into microcontroller inputs. All right, so now more interesting, analog input and output, also something that we talked already a little bit informally, or we looked at the circuit. Now, what does it really do? Well, here first a digital to analog converter. So what's the input? Well, the input is a binary number, and here in this simple example, it's a binary number that has actually 3 bits, okay? So it can go from 0, 0, 0 to 1, 1, 1, and anything in between, signifying then the decimal number 0 all the way up to 7, right? Okay, so now the digital analog converter takes these numbers. In this case, it's just only 7 different ones. It could be more if we had a, for example, 16-bit number that we wanted to convert. Here it's just 3 bits. Make my slide a little bit simple. It converts that to an analog voltage. Now, sort of reasonably, 0, 0, 0, we assign the value 0 volts. 0, 0, 1, we could assign, for example, 1 millivolt or 1 volt or whatever, right? And then 2 volts. Something like that, right? All the way up to 7. Right? So the input is this discrete number of values, because hey, it's binary. A digital system can represent only a finite number of cases, possibly very many, and then the output, of course, also will assume only a finite set of different voltages. Okay, and here is how to represent this in a formal way. So here is the input to analog converter, and this is simply the step size here, delta V. So that's the step going from one signal to the next one. Okay? So how would we do that? Well, we've actually looked. You remember that? We looked at this pulse width modulation DAC. Well, that was one way to do it. Another simple way to do it is, let's say you have here VDD, and here you have VSS. You take a long string of resistors, many more probably in practice, and then, of course, here you get VDD, here you have VSS, and in between you have values, well, in the middle, right? And so you put the whole bunch of switches here, and then using the microcontroller, you close one or the other of these switches, and that gets at the output an appropriate voltage that can be anything between VSS and VDD, and steps in between, right? Okay? So analog to digital converter, well, here we have just the opposite problem. Here we start with a continuous voltage V in, and then at the output we have a digital output, and that has a number of bits. And that number of bits is finite, right? Because no computer, not even the one with 4 gigabits of RAM could represent an infinite number of different values. So the A to D converter has to map a continuous quantity and a continuous voltage that can assume an infinite number of different values to just a finite number of digital codes. Yes?
On the previous slide,
Is there, can you speak up a little?
is there anything good about that design? Isn't it just wasting power?
Oh, okay, that there is always current flow. Yeah, well, maybe the resistors are high value if you want to go slow, and if you want to go fast, you need to make them lower value. But then if you want to go fast, it actually consumes power anyways. So no, actually, these are used. I guess the only bad thing is if you want an 8-bit digital to analog converters, how many resistors and switches would you need? Well, 2 to the 8 or 256. 256 or 255. Huh? Okay? Right? Because then you want to be able to generate 2 to the 8 different analog voltages, so you need that many switches and that many resistors to make that. Now, 256 isn't that terrible a number for an integrated circuit, no big deal, you can do that. When it gets to above 1,000, then it starts consuming so much area that other solutions become more attractive. But it's simple, and yes, up to 8 or 9 bits, this solution is frequently used. Yeah. So, but it's an integrated circuit, right? We're not gonna breadboard this on a protoboard, right? Yeah. There was another question? All right. So yes, it's simple. I guess the advantage of this is simple, and I've seen it I actually used one 30 years ago when I was in high school. I had to build something, so I used one of these, and it was done like this, and I liked it because I could understand easily what was going on. I've seen them also used in video outputs, right? You need the inside. There is the video processor, of course, produces digital information, and then the VGA port's actually analog, so you need to convert that to an analog number, and that's done with the DAC, and very often they use DACs that look like this. Okay, so again, the analog to digital converter now, right, going to A to D, the opposite. That one starts out with a continuous signal, continuous analog waveform, and it somehow needs to go then to a digital number, and so it has to go from an infinite number of possibilities to just a finite one, and there has to be some rounding, right? So if, for example, the input was here, well then we get this particular code here, but if the input was a little bit lower or a little bit higher, we would still get the same code, only if we make it even higher, and then we get the next code, right? So there is this quantization. And again, we can define sort of the bin width here as delta V, okay? And then we can represent the quantization simply by a rounding operation. Mathematically, that's really what's doing. Of course, there is no round statement somewhere in our circuits that does this, but that's what's happening. We've talked already about I guess no, maybe we haven't talked about A to D converter. Well, there is again, there is a very simple way to build. There are lots of ways to build A to D converters, but one that is particularly simple is called the flash A to D. Flash A to D. And so again, it uses a string of resistors to produce all sorts of different values, voltages between VSS and VDD. And then it has comparators. So these are things that produce only a 0 or a 1 at the output. It's like an op-amp, but it produces only VDD and VSS. And the comparators, there are many of these, they compare the different analog voltages that we generated with our resistor string to the analog input, Vin. Okay, and there are many of these comparators also, as many as there are resistors. Okay, so there are more of these, and each of them can be 0 or 1 or 1. Okay, and so now, if we think about when this operates, well, if we have a voltage that is 0, if the input voltage is 0, Vin, this one was 0, well, then we get all zeros at the output of our comparators, right? If then we slowly increase the voltage, well, the first comparator starts tripping and all the other ones are still 0. And if we make an input voltage somewhere around here, well, then we get most ones and only maybe the top 2 or so are still 0, right? So depending on the number, on the input voltage, we get few or more of these comparators turned on and therefore produce the right. If it's really cold, all zeros. If it gets warmer, more and more. Right? And then ultimately, if it's really, the voltage is really high, well, then we get the thermometers. So it goes all the way to the top. Okay, and then there is some kind of a digital circuit that takes this and makes a binary number out of it. Okay? All right, so I do not expect you to design A to D converters and so on. I just thought that you might find it interesting to at least have some kind of an idea that, yeah, it's possible, and how is it possible? I also say that because when I was in high school, I built all sorts of stuff like that, and I always wondered, but how in the world do they do this? How is it possible? Well, it's actually not that difficult. So what would we didn't learn a whole lot of new stuff here, but what would I like you to know now? Well, I would like you to understand or refresh us whatever about binary numbers, and I would like you to be able to convert between binary and decimal numbers. You probably learned that somewhere, otherwise there's a slide about that. We will just rely on you being able to do that. I also would like you to understand what a DAC is and what an ADC is, what an analog digital converter and what a digital analog converter is. I would like you to understand how they operate, and also would like you to do these transforms between the input and output of these devices. Then you will have to be able to write very simple programs, and I expect that you know that already from one of the 61 courses or whatever, what you did in high school or so. Okay? Are there questions? All right. So that's kind of the starting point that we will need to look at the digital systems in more detail. And I have another minute, so I would like to give you a preview of where we are going to go. So where we are going to go is we want to understand how do we actually implement digital computation. Let me see whether my slide. How do we implement digital computation? How do we do that? How do we, for example, make an adder out of electronic circuits? Okay? And then once we've built that adder, we want to know how fast does it go? How fast can that adder go? And then we would like to know how much energy or power does this adder need? And once we understand that, we will go and analyze stuff like, is it better to have one adder that goes blazingly fast, if we have to do a lot of computation, or is it better to have two adders that go at half the speed? And why? Okay? We're also going to look into stuff like, how do we build these things out of transistors? And what do we want from transistors in order to make good circuits? We will understand afterwards why it's such a big deal to make transistors smaller. It's not only because we can fit more of them on an integrated circuit. Okay, so that's going to be the next couple of lectures or so. All right? Have a good weekend.